Let me now talk about our last example of this class, which is Cournot with incomplete information. Okay. Now the idea is the following. So suppose there are two firms, so we'll consider duopoly. The market demand is given by P equals to 10 minus Q, where Q is sum of the total outputs produced by the both the firms. Firm 1 has zero cost of production, so firm 1 has zero cost of production. Firm 2, on the other hand, can be one of two possible types, right? So we'll say that firm 2's marginal cost is either 0 or 4, and it is 0 with probability half, and 4 with probability half. Okay. Now so basically 2's marginal cost is 0 times Q2, which is 0, or 4 times Q2, depending on which type it is. We will refer to the 0 marginal cost case as the second firm which is a low type. Low meaning the cost is low. So we'll refer to this case as L type firm, and we'll refer to this as high type firm 2, right? Okay. So what is the, if I have to just write down the extensive form, first nature moves and with probability half it either selects the high type or it selects the low type with probability half for firm 2. Firm 1 then moves and chooses Q1. Q1 is a continuous variable strategy, so that's why, so that's why we are writing in cone format. Importantly, firm 1 doesn't know whether the firm 2 is high type or low type, so firm 1 has a information set here. Okay. Firm 2 knows whether it's high type or low type, but firm 2 doesn't know the choice of Q1, right? Because it's a simultaneous move game, right? So here we will then write this dotted line to show information set, and firm 2 chooses Q2. Here again, firm 2 doesn't know choice of Q1, and 2 chooses Q2, and then payoffs are realized. So what is the payoff for firm 1? Payoff for firm 1 is 10 minus Q1 minus Q2 times Q1, right? Because cost, so this is the revenue. 10 minus Q1 minus Q2 is the price times quantity produced by firm 1, so that's revenue, also the profit, because firm 1 has cost 0. Same for firm 2, so 10 minus Q1 minus Q2 times Q2. Okay, sorry, firm 2 here is high cost, so here it is minus 4 Q2. So that's the total profit of firm 2. Okay, this is the payoff in the top node. in the bottom node, it's the same for firm 1, because firm 1 is always zero cost, and firm 2 here has zero cost. This times Q2. Okay, so this is the payoff. So this is the entire extensive form expression of this incomplete information simultaneous move game. Okay. Now, so firm 2's strategy will be type contingent. So firm 2 has a node information set here, has an information set here. So firm 2 will have to specify if it is high type, what will be its quantity production. If it is low type, what will be its quantity production, right? So firm 2 strategy will look like Q2H, Q2L for various values of Q2. Okay, so it has to specify this. Firm 1 on the other hand has only one information set. So firm 1 will choose Q1. Let me write it before. Firm 1 will choose Q1. Right, for its information set. It will only just say how much it wants to produce, because it doesn't observe firm 2's cost type. Okay. Now, given the probability is half and half, therefore each player can compute expected payoff. Okay. So what is the payoff of player 1? So let's compute payoff of player 1. When player 1 chooses strategy Q1 and player 2 chooses strategy Q2H for the high type and Q2L for the low type. Okay. What is the expected payoff? Expected payoff is with probability half. Player firm 1 expects firm 2 to be high type, in which case his payoff is price times quantity. What is price? 10 minus Q1 minus Q2H. Okay, Q2H, because with probability half is of type H, times Q1. So that is the profit for in the event that nature has moved high type, plus half times 10 minus Q1 minus Q2L times Q1. Okay. This, if you simplify, you will get that it is 10 minus Q1 minus half of Q2H plus, sorry, half of Q2H plus half of Q2L times Q1. Okay, so basically this inside the bracket is the expected production of the second firm. So from the expected profit, we see the expected profit expression of firm 1 has inside it, if you simplify, an expression for the expected production by the second firm, right? With probability half it produces Q2H, and with probability half it produces Q2L. So the expected production is this expression, half of Q2H plus half of Q2L, and profit of or payoff of firm 1 depends on the expected production. Okay, so this is because we have assumed linear demand function. In case it's a non-linear, we will not get such a nice simple expression. Okay, so this is the payoff, expected payoff of firm 1. Firm 1 would like to choose the best response, so would like to maximize this expected profit by choosing Q1 by fixing both Q2H and Q2L. So it imagines, let me take as given the strategy that this type contingent strategy of player 2 of firm 2, what is the best thing that I can do, right? So firm 1 would maximize this by choosing Q1 and fixing opponent strategy. Okay, so if I maximize this, what do I get? So the first order condition is 10 minus 2q1 minus half of q2h plus half of q2l equals 0, which gives you q1 equals 5 minus q1, sorry, not q1, q2h plus q2l by 4. So this is the best response of firm 1. Okay. Now firm 2 type H would also like to best respond. So what is the, so let me just mark it. So this is the best response of firm 1. Okay. So this, let's call it equation 1. What is the payoff of firm 2 of type H given the same strategy Q1 and Q2H, Q2L? This is basically, so basically payoff on the top node of firm 2. So firm 2's payoff is 10 minus Q1 minus Q2H times Q2H. It's a high type, so it has a positive cost, marginal cost, so 4 Q2H. So it will maximize this with respect to Q2H. Okay. And this gives you the first order condition is 10 minus Q1 minus 2 Q2H equals 0, which gives you Q2H equals 5 minus Q1 by 2. So that's the second best response equation. Similarly, there will be a third best response equation coming from the optimization by the low type of firm 2 for the same strategy Q1 and Q2H, Q2L. So here the payoff is 10 minus Q1 minus Q2L times Q2L. It's a low type, so marginal cost is 0, so this is the profit. So again it wants to maximize this subject to, sorry, by choosing Q2L. So the first order condition is 10 minus Q1 minus 2 Q2L equals 0, which gives you, oops, sorry, I made a mistake here. It should be 6 because there is a minus 4 here, so in the first order equation it would be 6, so it should be, sorry, 3. Yeah, and here it would be Q2L equals 5 minus Q1 by 2. So that's equation 3. So there are 3 best response equation, one for player 1 and 2 best responses for each of the 2 nodes of player 2. Right? Let me, if I go back, there you go. So here on the top node, player 2 is choosing Q2H, and on the bottom node player 2 is choosing Q2L, and each of those choices would have to be optimal, right? So each of them have to be profit maximizing, right? Remember, in that final node also you would have to choose given, so these are, each of these would have to be best responses. Okay. given this, we basically have to solve equation 3, equation 2 and equation 1. So we know the expression for Q2H and Q2L as a function of Q1 in 2 and 3, so we can substitute 2 and 3 inside 1. So suppose I do that. So one tells me that Q1 is 5 minus quarter of Q1H and Q1L, where Q1H is 3 minus half of Q1, 3 minus half of Q1, and Q2L is 5 minus half of Q2 plus 5 minus half of Q2, which so this implies Q1 equals 5 minus 2 minus a quarter of Q1, or 3/4 of Q1 equals 3, which implies Q1 star is 4. This implies Q2H star is 3 minus 4 by 2, so that's 1, and Q2L star is 5 minus 4 by 2, so 3. Okay, so what is the Bayes-Nash equilibrium? The Bayes-Nash equilibrium is, again, it is Q1 star, Q2H star, Q2L star, which is 1 comma, high type chooses 1 and L type chooses 3. Okay, so this is the Bayes-Nash equilibrium. Now notice that the high type chooses lower quantity, which makes sense because its cost of production is higher, right? So it is costlier for firm 2 of high type to produce more than firm 2 of low type. So in equilibrium you see that firm 2 of low type produces more than firm 2 of high type. Okay, and these are mutual best responses because they solve the 3 best responses arrived at from the first order conditions. Okay, and therefore this constitutes a Nash equilibrium. Why it is Bayes Nash equilibrium? Again, because we use these probabilities to compute the expected payoffs. Okay, so so let me stop here. This gives you a broad sense of how to compute Bayes-Nash equilibria. We will continue this discussion for the Thursday session as well, and we'll cover more examples and applications to sort of help you get used to this concept. Okay, thank you.